So I'm going to explain box 8.2, and this is designed to illustrate how biological processes affect current flow over the seabed and also oceanographic processes. So in this diagram we've got two different scenarios. We've got a muddy seabed over here with a lot of microbiology producing what are known as extra polymeric substances. Now this creates microbial infilling. If you like, it's the slime that makes the surface very smooth. Now when you have this very smooth surface, what develops is a laminar sublayer, otherwise known as a boundary layer. This can form a physical barrier to exchange between the sediment and the water column above. And above that boundary layer we have a laminar flow. So the way to think about this is think about the water column sliding over this very thin layer of water at the seabed, at the sediment-water interface. Now, what happens when you have larger organisms settled onto the surface of the seabed, or organisms protruding from the seabed, is they create roughness elements. So here we see a transition to a mussel bed. So the mussels protrude from the surface of the seabed and they create roughness. That roughness creates friction and sets up turbulent flows, turbulence basically, that disrupts the laminar flow passing over the mussel bed. What that then does is it accelerates the rate of transport of particles from the water column above down to the mussel bed. So in many ways this is a positive feedback mechanism because of course the mussels are feeding on phytoplankton and particulate matter which is flowing from the surface down to the seabed. So in other words, they accelerate the transport of food to themselves. We can illustrate that further looking at this study, which effectively followed a cylinder of water, so the same cylinder of water, over part of the tidal cycle. This is the water column from the seabed to the surface. The tide is rising, so the height of the water is getting higher and higher. And the coloration in the water represents the density of phytoplankton, concentration of phytoplankton in the water. Now the mussels are all at the seabed, and the area closest to the mussels shows that it's depleted of phytoplankton, which is not a surprise. So the phytoplankton most concentrated towards the surface, where obviously there's more sunlight, and the phytoplankton then sinking slowly to the seabed where they're filtered out by the mussels. Now what happens as the cylinder of water is moving around with the tide, you can see that there's quite good replenishment of the phytoplankton in the water column through primary production. However, at this point in the diagram, the tide is starting to slow down. So you start to see that the mussels are making a much bigger inroad into the column of water, drawing down more and more of the phytoplankton, until eventually we get to this point of the diagram here, where basically we have slack water. And at the point where we have slack water, the water is not moving around over the mussel bed. So basically the turbulent flow that we talked about before is not occurring. And what's happening is because of the mussels' filtration activities, they draw down all of the phytoplankton in the water column above. So at that point in time when the tide stops, the water column becomes completely depleted. So the fact that we have tidal currents and tides moving across mussel beds is incredibly important because what it does is it prevents complete depletion of the water column above. But we just get this little window into the physical processes when slack water occurs, and we can see what happens when we have a low energy system, i.e. a slack water. And we can really see the influence of how potent mussels are as feeders on the phytoplankton community.